today's speaker, Professor Kouwenhoven of the Kavli Institute of Nanoscience of the Delft University of Technology. Professor Kouwenhoven has been at Delft since he started his master's studies in 1988. He promoted to PhD cum laude in 1992, and he's been a full professor at Delft since 1999, where he leads the quantum transport group. So Professor Kouwenhoven's group is well known in the condensed matter community for many experimental achievements in fabricating and measuring the properties of tiny quantum devices, such as, for example, qubits, which are the building blocks of quantum computers. And for this research, he received dozens of awards and honors, perhaps most notably the Spinoza Award in 2007, which is the most important Dutch scientific honor. And besides the fundamental science, he's also the founding director of the QTech Advanced Research Center for Quantum Technologies, which was founded at Delft campus in 2013. And the QTech project's main goal is to create a first working prototype of a quantum computer in 6 years with the combined efforts of leading scientists and the high-tech industry. So this QTech innovation was jump-started by recent breakthroughs, which reached the climax in 2012 when its group published the results of a series of experiments in science which showed for the first time signatures of exotic quasi-particles known as Majorana fermions in a very complicated device which was proposed by theorists 2 years earlier. And for its discovery, he gained a lot of attention also from a wider audience. And he made a noteworthy appearance in the Dutch media where he explained his discovery on a popular talk show using Duplo bricks to kind of create this device. And okay, so what these Majorana fermions are and how they relate to quantum computers is the subject of today's talk, the quest for Majorana particles.
Thank you very much. That was a very nice introduction. I was actually born in Delft, so I've been all the time not starting at the master. There was one thing I want to correct. I also want to maybe more important that the other thing that you mentioned, that in Holland, cum laude actually means something. We don't have the summa, so that yeah, it is something that I'm proud of. You also said we promised 6 years for building a quantum computer. I'm not sure that we're going to make it. So don't tell anybody else, but have to be careful. But today's subject is about Majorana fermions, Majorana particles, and we're hunting for this very special particle. And we're actually doing that in competition with particle physicists who are looking for Majorana fermions as a cosmic race. And to detect the Majorana fermions from the cosmos, they are building huge detectors in caves inside mountains filled with liquid that is sensitive to scattering events with possibly a Majorana fermion. The approach that we have is completely the opposite. So our detector is very small. This is a huge zoom in on our device. It's, in reality, it's less than a micrometer, so you cannot see it with bare eye. And also our team of people is not a big group of particle physicists. It's about 10 people who can do the experiment. So it's an entirely different approach. Nevertheless, it's interesting that we are hunting for a particle that was predicted by Mr. Majorana, Hector Majorana, in 1937, I believe. It's a long time ago. And since then, mostly the particle physicists have been hunting for this Majorana fermion. It's a very simple definition, and it's given by this symmetry relation that it says actually that the operator to make up the Majorana fermion is the same as the operator to delete it. Or in other words, in this sense, is what it means is that the particle, the Majorana fermion, is actually equal to its own antiparticle. Now, if you have this symmetry that the particle is the same as its antiparticle, it means immediately a few things. Because if it would have a finite energy, then the antiparticle would have the opposite negative energy. Or if it would have a finite charge, the opposite antiparticle would have, the opposite charge. Spin, same story. So this symmetry already tells you that it's a particle that has a lot of nothings. Right? The energy is 0, the spin is 0, the charge is 0. The symmetry is actually okay for bosons. So a photon or also a Higgs boson is its own antiparticle. It's special for fermions. And then it becomes something that we haven't seen before. Now, given the fact that everything is 0, how do you actually detect a particle with everything 0? And that makes it so difficult also for the cosmic Majoranas to actually get an event click in your detector. There's two nice reviews from Frank Wilczek, an authority, Nobel laureate in particle physics, who wrote 2 reviews where he actually makes the connection between the cosmic Majoranas and also the condensed matter Majoranas. How similar they are, but also, there are also many aspects where they are different. Now, the fact that the particle was predicted in 1937, and everybody has been looking for it for so many decades, is actually there's actually a kind of a sad analogy also with the man who predicted this particle. Because the man, Majorana, 1 year after he predicted this particle, he disappeared himself. And so he just left. He actually was working in Naples, and he took the boat to Palermo. Before he took the boat, he actually took all his cash from the bank. That's kind of suspicious. You take all your cash from the bank. And then took the boat to Palermo. He bought a ticket, but that's the last thing that people had seen of him. And this little piece in the newspaper asked, did anybody see Ettore Majorana? Piece that was in the newspaper in 1938. And literally, I'm not sure if there are Italian people here, but people are still making Italy. He's world famous in Italy. So there are still documentaries, books being written, or all kinds of conspiracies where he could have been since 1938. And really, it is still alive, that story, because if you can read Italian, this is actually a screenshot from the website from an Italian journal from last week, 2015, February, where, you can all translate this. Ettore Majorana, the prosecutor of Rome, says that he was still living between 1955 and 1959. And people have seen him, that he was identified in those years, and now the prosecutor in Rome has made it official. Now, you can also read this text. It actually says some famous names. I actually know what it says because there's also an English translation. And this is the news from last week. Apparently his disappearance, his disappearance was not a suicide according to the Rome prosecutors. He was just, hiding somewhere. So the story is still on. And at the end of this presentation, I actually also have some news about the man, Majorana. This is last week's news. We have some even more recent news about Ettore Majorana himself. But physics, we want to have his particle. What do we know about particles? Well, particles are actually, the definition of a particle is actually that they must be a solution of the Dirac equation. That's the definition of a particle. They only exist because they are solutions of the Dirac equation, with one exception, and that's the one that Majorana proposed. He slightly modified the Dirac equation and found a new solution, a solution where the operator to make the particle is the same as the operator to the Dirac. In terms of symbols and operators, you can write this. Actually, if you have this C dagger, it means that you have an empty state and you have this operator acting on the empty state, then you fill it with one fermion. If you have the annihilation operator, that it operates on a filled state, you actually empty it. And that's all you basically need to know. And you know that quantum mechanics has solutions which are complex numbers, and that makes it so strange. So you can write those, also those operators, as a complex number. And there's a real and imaginary part. And you know, this operator for creating, for instance, let's take an electron as the example for fermions. This is the operator to make an electron, this is one to annihilate or create a hole. Now, not doing anything special, just rewriting these two little equations, you can express the gamma in terms of the fermion operators, or the gamma is also this gamma 2 in terms of these fermion operators. And it's this operator, gamma 1, and also this operator, gamma 2, that are our Majoranas. If you check, if you take the complex conjugate, then you see it's actually equal to its self-adjoint, as I say. Both for gamma 1 and gamma 2. So it's just rewriting the normal operators for making fermions, and expressing them in a new way. You get the Majoranas. And if you look at this gamma, there's a factor of 1/2 in front. But loosely speaking, a Majorana is half an electron. So what is so special? I mean, if it's just rewriting a complex number, what is special about it? Well, it's not special at all. It's very trivial, unless you can do something special to it. So suppose that you have one fermion, like an electron, and you can break, it's an elementary particle, so you cannot do it, but imagine that you can break it in 2 pieces and bring the 2 pieces apart. And for instance, if this one piece has, the electron also has, the electron also has an internal momentum, the spin. If you can break it in 2 pieces where the upspin goes here and the downspin goes to the other side. That would be very interesting because the spin flip, usually on a single electron, is very easy because that single electron can flip just by turning its magnetic moment. But if you separate the spin up and the spin down states, it becomes very difficult because scattering or flipping its spin requires as well a long travel, a long jump over distance. So if you can do something like that, you have something special. If you can break the particle in 2 pieces, put them far away, then they have become a new particle, we call it a quasi-particle, and we actually do it in solid state. And what you require is some kind of topological properties, in this case, topological rotation. There are some keywords here, and these keywords I like to give you some examples, or explain a little bit what the meaning is for condensed matter physics of topological properties, quasi-particles, and also what it means to be an emerging state arising from collective behavior. And you can also read about it. There's some reviews. There's also a very nice one in Physics Today from 2012, written by one of the early theorists in the field, Nick Reed. Now, first of all, topological properties. We have some examples of topological systems. The simplest classical one is the Möbius ring. You just make a twist in it. And if you deform the ring, the number of twists in the ring doesn't change. It's protected, the twist number is protected against small deformations. You really have to cut open the ring and reattach it to change the twist number. Now we actually know of a similar effect in what's called the quantum Hall effect, where you have a 2-dimensional system, magnetic field. Then if you measure its electrical properties, what you get is a graph like this. This is the resistance. This is actually the function of magnetic field. It's very complicated stuff here, but if you look at these this is the Hall trace resistance, then you see these flat regions. These are plateaus. And the beauty of the quantum Hall effect is that these values at these plateaus are quantized. They're quantized at exact values of h over e squared, Planck's constant divided by the electron charge squared. And exact, at least with an accuracy what people have measured today, is about 10 digits. So this is a quantum effect. It is the resistance is quantized at the units of Planck's constant. There's nothing, what can be more quantum than Planck's constant? And the beauty is that it doesn't matter how big the sample is. It doesn't have to be rectangular. It can be any shape, any size. It's independent of size and shape. And that's what makes the system topological. You can make it 2 times bigger, but this Hall resistance quantized at this h over e squared stays the same. Now you can think of these transport properties, if I go back, as that the current flows actually only at the edges of the sample, and then it doesn't really matter how much spacing is between these two channels at the edges. Now the similar picture for one-dimensional systems, that's what we will be looking at, is like this. That instead of, I've already shown you this picture of this electron broken in two pieces in one dimension, that in a one-dimensional system, the two interesting pieces are at the two ends of the system, and independent of the length in between them, that doesn't change the state. It's all the properties are completely determined by the end states, and the piece in between doesn't matter anymore. So that will be actually our thing to study today. Okay, what else we have? Collective behavior. Now this, I cannot make it any simpler than to illustrate the collective behavior by a train. As a train is a collection of wagons. The wagons are all connected together. The wagons therefore can no longer freely move themselves. They're completely locked in one single motion of everything moving as one full train. If I'm looking at excitations of this train, if I want to perturb this system, then I can try to kick out one of the wagons in the middle, but that will be a high energy excitation. You will find your low energy excitations at the first or last wagon of the train. These are easier to disconnect. So a one-dimensional system, and this is actually a pretty good prediction for one-dimensional systems. For one-dimensional systems, you will find these excitations somewhere at the ends. If I connect this to electrons, and electrons are filled orange disks here, and I have a one-dimensional wire, and I fill up the one-dimensional wire almost completely except one state. So you can think of it as seats. All the seats are occupied except the one over here. This is an empty seat, and that's what we call a hole. Now we can ask the electrons all to move one seat over, and that means that the hole, in effect, jumps over a large distance. And so everybody moves over a little bit, the empty seat goes to the other side of the room. So that's what collective behavior can do. You have a whole state, and that's filled, creating a whole state on the other side. If it happens fast, it goes back and forth, that whole state. And we know that something that goes back and forth fast, then in quantum mechanics, it can also be in a superposition. That's a classical picture. Superposition would be that the whole would be on the left and right side at the same time. So again, I started to think about the whole jumping back and forth. I can do a new, say, transformation. I think about the particle, and now I see, if I just look at this particle, that it's actually a superposition of an electron and a hole. So instead of a spatial superposition, it's now a particle superposition. Where this piece at the end is half an electron and half a hole, and to conserve particle, we also have one on the other side. Now that particle, that is exactly our Majorana. This symbol in my talk will be the equal superposition of an electron and a hole. That's our Majorana. Now, you can actually show, and I will give you an example, but what you need to make this exactly half, so an equal superposition, you actually need a superconductor and a magnetic field. But under the right circumstances, you can mathematically show that these two objects are indeed Majorana fermions. Now, this is a cartoon picture. If you wish, you can also look at a Hamiltonian with superconducting correlations in a Hamiltonian. That was done in a beautiful, actually still simple paper by Alexei Kitaev from 2001. And what you see here in this figure 2 from his paper is what Cooper pairs can do. You probably know that in a superconductor, electrons are paired in a Cooper pair, so they're charged 2e, and they move, as an object, as a solid, 2e object. Now, how can you pair up? There are actually two ways to pair up. You can pair up by, for instance, hugging somebody, and then you are a pair. Or you can also maybe hug or pair up, and you just cross, you put your arms in each other. And there's an important phase transition if you go from hugging to connecting by arms. If you're hugging, yeah, then you're connected to your partner. And if we have an even number in the audience, then everybody can be connected. It's good. If you connect by arms, in a line, then there will be an empty arm on one side as well as an empty arm on the other side. Again, and these are the two excitations from the train, and it's exactly this type difference in pairing that gives you in the end one type of superconductor or a different type of superconductor. And this is the one that has the Majoranas at the end. If you're a superconducting specialist, this is what we know as an S-wave superconductor, and this is what we know as a P-wave superconductor. And I'll come back. But it really comes down to the precise way of pairing mechanism between electrons. All right. This was sort of Kitaev, but if you look at Kitaev's paper, it's really mathematical. There's a Hamiltonian, there's some tricks in the mathematics, some transformations, and I didn't read that paper in 2001. I could have tried, but wouldn't have made much of an impression on me. But then there were some papers, particularly these two papers, Luchin et al. And Orat et al. That appeared in 2010, that translated the Kitaev proposal into a more practical proposal, where they could really literally write out, do this, do that. We give you a recipe, and if you make it, apply a magnetic field, then there should be Majoranas in your system. And there were 4 ingredients in this Majorana recipe. One is that you need a one-dimensional system. 2 is that you need spin-orbit interaction. 3 is that you need superconductivity, and you have to apply a magnetic field. So what I'd like to do is you go a little bit through these 4 ingredients separately before we put them together and get to the Majoranas. Now, starting with one-dimensional systems, we are collaborating with material growers in Eindhoven, Erik Bakkers and his group, that grow semiconductor wires out of a catalytic particle. And they can be long and skinny wires. This is a particular example of indium and timonite wire. They have a certain crystal structure. They grow along a certain axis, a few micrometers long, and the diameter is between 50 and 100 nanometers. Now, we particularly choose this material for reasons that I will explain in a minute. That is that this special semiconductor has a very strong spin-orbit interaction. Now we take these wires from Erik Bakkers and we make a very simple device out of it. And we put it on a substrate, we make contact to that single wire. There's actually a gate electrode underneath in the system, somewhere in the substrate. So you can do a measurement of the electrical properties as a function of the gate voltage applied to this gate. This is a picture of the device taken after the measurement, and you actually see that after measuring it, this piece of nanowire in the middle is actually blown up. So it acts like a fuse. If you don't treat it carefully, it just evaporates. If you measure the conductance from here to here through the nanowire as a function of the backgate voltage, now what the backgate voltage does, if you make it more negative, it just pushes away the electrons. At some point, there are no electrons left in the wire. The conductance should go to 0. It spins off. And indeed, the conductance goes to 0. Interestingly, you see that there's a little plateau, very similar to the quantum Hall effect, but now it's 0 magnetic field at a particular value. And we've taken these measurements at 10 different devices or so. And all of these devices, they all have their own characteristic, their own personality, but you see a plateau at this value in all these devices. And there's also signatures of the second or the third plateau. What it means is that what we can read off from these measurements is that the transport actually in this system is quantum. There are quantized states in this nanowire, one-dimensional subbands, and the conductance through a one-dimensional subband is actually 2e squared over h. This is still in current, but if you translate it to conductance, you get exactly the value of 2e squared over h. And you see that all these devices give you the same value. I'm actually showing here and there some data on white slides. That means that's very fresh data. This data was taken last few weeks ago or so, not published, not polished. It's really fresh. So if I show data on a white slide, it's fresh. And if it's colored and massaged, and may look good, then it's probability. But this is actually a very nice result. Okay, next is the spin-orbit interaction. And spin-orbit interaction is simply that the electron has a spin, electron has an orbit or a motion, it can move. And in materials with a spin-orbit interaction, then when it moves, the spin also rotates. Right? There's no spin-orbit interaction, but with spin-orbit interaction, it just moves. You can also say that the spin or the orbit by themselves are no longer good quantum numbers. There's some mixture of spin and orbit that becomes a good quantum number, crown or state. So what is the spin-orbit interaction in this system? What does it do? Well, if I have a one-dimensional system, it can only propagate in one direction the electron along, let's say, k direction, positive momentum, or negative momentum. This is positive, this is negative momentum. It moves as a free electron, so it's a quadratic dispersion, energy versus k. And if nothing special, then the spin up and spin down states are degenerate at zero magnetic field. This spin-orbit interaction, what happens is actually that the spin and the orbits become coupled, such that the up spin is coupled to the motion in, let's say, with a positive sign, which moves this parabola to the left, and the down spin with a negative sign, which moves the parabola to the right. Shifting the two parabolas, there's now a single point only where they have an overlap. But if I apply a magnetic field that has under a particular angle, then these two states start to mix up, and you create a gap right at that point. So now I only have 2 points here. For instance, if I fill my system with electrons such that the Fermi energy is right in this gap here, that means that at the Fermi energy, all the electrons that move to the right, positive momentum, have spin down. And all the electrons that move to the left have spin up. And so spin and momentum is now completely correlated. They move this way, they move the other way, and they separate. Now this is something that, this effect of the subbands and how strong is the spin-orbit interaction in indium and timonite, we've measured in some experiments, actually not so long ago, this is from 2014, doing weak localization and anti-weak localization measurements. But the upshot is that at the end of the day, we measure a value of about 1 millielectron volt for the spin-orbit interaction. That translates to a distance of about 50 nanometers for the electrons to travel to change the spin by pi. And that's this number, 1 millivolt, corresponds to 50 nanometer in spin-orbit length. That's a number, if you compare it to temperature, that's several Kelvin, maybe 4 Kelvin of temperature. All right, so next is superconductivity. What can we say about superconductivity? Well, first of all, is that in a superconductor, I already said that electrons are paired and in a Coulomb pairs, but there's an underlying symmetry in a superconductor that is obeyed by all superconductors. And that symmetry is given here is that if you create a particle, an electron-like particle at a positive energy, then there must also be a state at negative energy, at exactly the same energy. And there is an opposite state with a whole character at the opposite energy of the electron state. So this is like a particle hole, in this case, electron-hole symmetry relation. So you can say, okay, that's a great starting point because we want this at zero energy. But so if we start here, then somehow maybe we can make it go to zero energy. And then we are in business. Now this symmetry relation, actually, if you know what Andreev reflections, this sort of a picture over here is that the sum of an electron at positive and negative energy can create a Coulomb pair in the condensate of a superconductor. Good. Now there were 2 people, they found a trick. So it's basically an open question, right? This is a symmetry that superconductors have. If you want it at zero energy to get a Majorana, how do you get it? And there were 2 people, Fu and Kane, who came up with a good idea. Now here's the following. First of all, an example where it doesn't work. The example is actually starting with a superconducting film. This layer of superconductor S extends in this direction. It's a film of superconductor. You apply a magnetic field, and it creates pockets where it can penetrate some magnetic flux lines. And these pockets are known as vortices, and they are regions where the superconductor becomes normal, and where the field can penetrate. Now the superconductor, if I now have an electron in this normal conductor bouncing back and forth against the superconductor, it cannot simply enter the superconductor, it is reflected by the gap. Now this reflection by the gap we actually recognize immediately as a particle in the box problem, but now the walls of the box are formed by the superconductor. If you solve the eigenstates of a particle in the box, then you get some values. But the important point is that there's always a 0 point energy. And there's always this factor 1/2 that you cannot reduce to 0. And there's always a finite vacuum fluctuation or 0 point energy that lifts the lowest energy state to a finite value. These numbers, or these red lines, are the particle in the box states that we know, from the textbook examples, and the mirror symmetry is from the property of the superconductor, that you use superconducting walls instead of not superconducting walls. Now, Kouwenhoven, what they thought about was that if you make your walls special, and meaning special in the sense that if an electron bounces off the wall, it actually also gets a phase shift going back, and then get another phase shift going back. So it forms a standing wave with additional phase shifts picked up by a special superconductor. Then they found a solution where there was actually a single state at 0 energy. So then the question is, what kind of walls do you need? And they found that you need a wall that's made out of a P-wave superconductor. That gives you, as a solution, a state at 0 energy. Now, what is a P-wave superconductor? They may exist in nature, but nobody has found a P-wave superconductor from natural material. But the idea is that in a normal, what's called an S-wave superconductor, the Cooper pairing of two particles is accompanied by having two particles with opposite spin. So the total spin of the Cooper pair is 0. That's an S-wave pairing. Whereas in this case, the Cooper pairs pair again still up, but then with the same spin. And that also has an effect on the orbital part of the superconductor, and that's then called a P-wave. So not existing in nature, but yeah, okay. At least we have changed the problem from finding Majoranas to change the problem finding P-wave superconductors, and then go from there. That may be simple. Now we have been studying superconductors for a long time in Delft. I actually know also many people here in Antwerp have been studying superconductors for a long time. We've made some nano devices already 10 years ago, where we have aluminum as a superconductor. These three stripes are aluminum contacts. Here is a semiconductor nanowire. What we found is that you can actually send a current of Cooper pairs, a supercurrent, via this non-superconducting semiconductor nanowire out into the other superconductor. And you can do that over distances of about a micrometer. And so you do the experiment, you send the current through the system, and what you find is that even up to 100 nanoamps, a significant current, the voltage across the sample is still 0. So there's no dissipation at all, although the Cooper pairs have to traverse almost a 1 micrometer. We have up to 1 micrometer distance in the semiconductor. Now, at that time, I wish I had read, because it was 2005, the Kitaev papers, but I had no knowledge of Kitaev, so we actually stopped this research. We thought, okay, boring, let's do something else. So then in 2010, the recipe from Orek and Luchin came, and we picked it up again. So now we're making, again, similar devices. They are a little different, but similar devices, to study again how superconductivity can be introduced into a semiconducting system. Here's one example. Blue is a superconductor, niobium titanium nitride, very good superconductor. Critical temperature is like 15 Kelvin. We have the nanowire, indium and timonite, and we make contacts to it with gold on this side and also on this side. And what you see in this substrate in the back, I hope you can still see my pointer, are the gate electrodes. But these you can change. There you can change the potential, the voltages to make all kinds of potential landscape in your semiconductor. And in between, actually between the gates and your gold and your wire, there's a dielectric, so there's no leakage from gate to your nanowire. If I now may do a measurement from here via this nanowire out into the superconductor, then what you see is the following. Again, this is a white slide. Probably 3 weeks old, this data. It's a differential conductor. It's a function of the bias voltage between this normal and superconducting contact. At small voltages, electrons have difficulty to get into the superconductor because they have the superconducting gap right there. But at finite voltage, in this case about half a millivolt, they suddenly can go in, and then there's a normal conductance right there. Also on the left side, big T, but in between, you probe actually the superconducting gap in the system. If you take this measurement now as a function of magnetic field, so now the color is the differential conductance. You change the magnetic field, then the gap starts to close to smaller values, and there's still something left here, but not much anymore. So there's superconductivity up to about, I don't know, 1 or 2 Tesla, somewhere in between. There's another measurement, because this measurement with this gap, that you only have when there's a tunnel barrier in between the gold and the niobium superconductor. It really has to be an insulator between the normal and the nanowire in the superconductor. If you take away the insulator, let me just briefly give you some without maybe explaining too much, some data that if you take away the tunnel barrier by changing a gauge voltage, so here we have a tunnel barrier, but here we have a lot of conductance, then there's this very interesting region of red. If I go to larger voltages along this vertical axis, you see there is a better, more visible. This one has no knobs. So we, yeah? No. Experimentalist. I'm getting curious. All right. Somebody figure this out. Tell me when it works.
It works.
Oh yeah? So it was really. Yes. I have the solution. Somebody broke it down. Yeah, but that's not so complete, right? You figured it out, but it's not really usable. I'll try to use my hand. And this is actually an interesting region, because I know what the color scale is, and I give you a line cut through here. First I give you a line cut through here, and then I give you a line cut through here. These are traces that we, you can much better see what's going on. Again, it's the conductivity, differential conductance in units of E squared over H. And if I go into a normal state where superconductivity no longer plays a role at larger voltage, then I see again a nice quantized plateau in the system. If I turn on superconductivity, thank you. If I turn on superconductivity, then you see the black curve that at the location of the plateau, there's more conductivity. That is an enhancement. And this is what people know as the Andreev reflections through a point-on-point contact, where instead of having these charges, single electron charges going through this point-on-point contact, so there's 2e charges, and that enhances the conductance. In the ideal case, by a factor of 2, it should go up here, and here it's somewhere in between. And this is actually another indication that the wire is clean, and the temperature nanowires are very clean because there's a quantized plateau. But also the superconductivity is very well developed, because this tells you that the transmission of Andreev states into the superconductor has a very high probability. You can actually deduce a probability of 90%. Okay, so what do we have? We put all these things together. Then we have a nanowire, we have a gate electrode right there. And I think about the energy landscape and the field states. Then I have my tunnel barrier, I induce a tunnel barrier here. The states are all filled up to the Fermi energy. In this section of the nanowire up to here. Here at the end of the nanowire, the potential, of course, shoots to infinity. There it stops. If I make a connection to a superconductor, then the superconductor sends compares into the nanowire, which opens up also the superconducting gap. So now the landscape is like this. At the Fermi energy, you have a superconducting gap. But at the end of the system, of course, this gap goes to zero. There are no electrons, so that, you cannot open up the gap out of it. Also on this end. And we know that at this end we again have this particle in a box situation where electrons can bounce back and forth, make a standing wave or an eigenstate at some fixed energy. At a normal, let's say zero magnetic field. We can now also apply a magnetic field under the right angle, defined by this Kouwenhoven interaction. And this superconductivity is no longer an S-wave superconductor, but becomes a P-wave superconductor. The magnetic field makes sure that instead of having this pairing, you get components with this pairing as well. And this pairing, this P-wave superconductor, we call it a topological gap, now has end states of Majoranas at the beginning and at the end. You cannot have anything else but with this zero energy solution from full and K right there at the Fermi. And these are our Majorana states. All right, this is what we want to measure. This is how the sample box actually looks like. In reality, this is about a centimeter. We have our nano devices and our wires somewhere in there. These, different samples on the same chip. Then you put it in the chip box and you connect wires to it, and that goes into your dilution refrigerator. That goes to low temperature, 10 millikelvin or so, and then you start measuring. And the measurements, to explain the measurements, we do a conductivity measurement where we have in green, again, our nanowire. This is the superconductor. This is a gold electrode. Here is where we expect our Majorana fermions. In the gold, of course, we have normal electrons, so it's a full circle. And in the superconductor, we have group pairs. How do we get current? Well, we send an electron from the gold towards this point where it has to somehow combine with a Majorana and form a group pair. How can one electron combine with half an electron into a group pair? Well, if you remember that the Majorana is a superposition of an electron and a hole, then you can, if this electron picks out this part of the superposition, then it can form a group pair. And so everything is conserved in terms of particles. So the measurement, this is the energy landscape. You may have noticed that I speed up a little bit the time. The energy measurement of the measurement, electrical measurement at zero magnetic field, so differential conductance, voltage across the system. You see that again, because of the superconductivity in this region, there is a suppression of conductivity right here. It's not all the way to zero, but there's a clear suppression. And here again are the edges of the superconductor and where the gap stops. And this is the superconductor, here's the edge of the superconductor, and in energy it's like it's this peak. If I now turn on magnetic field and take many of these traces, then you see that something is changing up to half a Tesla. First of all, you see that the gap sort of stays. You can see this peak. But most importantly, around here, and let me highlight it, around zero voltage, zero energy, a peak starts to appear. And this is a super important peak because the peak is at zero energy, as you can see. But maybe even more important, more characteristic of this peak is that if you change magnetic field from this value, 50 millitesla, to a few hundred millitesla, the peak doesn't change position. It doesn't change energy at all. And suppose there would be something underlying this peak that would have a spin, a magnetic spin, and if you apply a magnet close to it, it will change its energy. It will get some kinetic energy or some energy from the interaction with your magnetic field. So the fact that this peak stays at zero means that the underlying mechanism has no internal degree of freedom that is associated with magnetic moment. And that's the conclusion. No magnetic degrees of freedom. Now I can take one of these curves and do a similar experiment. Now change electric field. Where we have all these gates, we can change electric fields. And what you see again is that the peak stays at zero. And we're changing the electric field here by a lot. The strength is, it's changing the density of the electrons by a lot, but the peak stays at zero. So whatever it means, the underlying origin of that peak has no electric degrees of freedom. It's not electrically charged. So here we already have three of the things that we're looking for found in this experiment. Is that no magnetic moment, it's a zero energy, and no charge. And these are these three characteristics. Now you can do many measurements, and that's what, also in this paper, and also in supplementary, there are many, if you're interested, go to the paper and look at all the data to decide for yourself whether all these measurements are consistent with a Majorana interpretation. That's what you can do, but I would like to use the remaining minutes to show you a few more recent data sets. So the peak that we had in 2012 was a nice little peak, but not very big. It would be nice to improve our system to get a peak that's actually theoretically should actually go up all the way to 2 e⁻⁸, and it means that compared to what I showed you, it will be 5, 6 times, maybe even 10 times bigger. And that means work, right? Because the peak is not doesn't reach the ideal limit because of some imperfections in your sample, which you then have to go after, look for it, do the right diagnosis, and improve your materials and your fabrication. We've been lucky to have some, we could go to a company with FEI, with a very good microscope, and what we found is that if you take a cut through the sample, you can actually still see the nanowire with hexagonal structure at the bottom. I hope you can still see it there. But the top is rounded off. And the top is rounded off because, before we put up the superconductor, we clean it a little bit with etching, and that makes the top rounded. And this rounding of the semiconductor decreases the quality of the induced superconductivity. So we've been working hard, and there has been a very nice result from our collaborators and friends in Copenhagen to make the connection between the superconductor and the semiconductor perfect. They have had a huge success by reaching the limit of epitaxial or atomically precise connection between the superconductor and the semiconductor. If you look at all these dots, these dots are atoms, and you see that the pattern of dots on this side and the pattern of dots on that side are correlated. There's an angle here, but you can see that there's a matching of these two crystal structures. And this gives you, it turns out, a very beautiful superconducting gap inside the semiconductor. Now to show you some quick scans of data if you improve the sample. It's all in color code, so I hope you, if you've never seen it before, it's probably very difficult to understand what you're seeing, but enjoy the red, white, blue color. It's conductivity, the IDV is a function of magnetic field, and here's the bias voltage. At zero magnetic field, there are just two peaks, which are these, these Andreev bound states between the induced superconductivity and the tunnel barrier. If you change magnetic field, they come together, then go to zero. This is the point where the Majoranas start to appear at zero magnetic field, and at 5 magnetic field with a zero bias voltage. And if you look closely, there's some structure. If I change the orientation of the magnetic field, not along the axis of the wire, but perpendicular to the wire, up into, let's say, the z direction, then it's different, definitely, but it's kind of similar. There's splitting here, stuff at or near zero down there. If I change it in the y direction, and in the y direction is actually the direction where also this spin-orbit interaction. This spin-orbit interaction you can also associate with a vector, and that vector I've already used it but not explained it. This is vector BSO. If you put your external magnetic field along the same axis, then this whole idea of creating this gap or this helical structure doesn't work anymore. So there should not be any Majorana if the magnetic field is oriented along BSO. And indeed, as a function of magnetic field, with the amplitude of magnetic field in the y direction, this state actually goes to zero, but it doesn't stay at zero. It just crosses, and then it goes again to finite energy. So indeed, if you don't expect it, there are no Majoranas. This is another set of data. Sometimes it's easier to look at, let's say, these curves compared to the color plots. But actually, with this resolution, it's also not so easy to see. But here you see a peak appearing. If you, out of this zoo of peaks, which are at 5 magnetic field, you pick a nice curve, you see that indeed by improving these materials and interfaces, the peak is now a lot bigger than we had before in 2012. And this is now 2 or 3 times bigger than the background in the normal state. It really exceeds it, whereas before it was an inside back a small piece. That's a significant improvement. This thing about the angles, that it shouldn't be there in a certain directions of magnetic field, but it should be there in other directions, you can explicitly test by rotating the magnetic field. So if you have your nanowire in this direction, and I change the magnetic field in a plane xz, that is let me see, xz that is out of plane, that's in this plane. Xc is in this plane, whereas the BSO points in this direction. So you always, if your magnetic field perpendicular to the BSO vector. And indeed, what you see for all angles from 0 to 2 pi, you see the 0 bias peak, sometimes a small splitting, always there. If I do it in the other plane, so now I do it in this plane, I sometimes hit the value for the same direction as BSO, then I only see the 2 discrete points. And so you see that there's a huge and distinct difference between the directions, the direction of the field, what you measure. And this is a very significant and characteristic property of these Majoranas in this system, according to this recipe from Luchin and others. So what do we have? And we follow the recipe. We've not, we've avoided doing anything creative or smart. And we follow the recipe. We have the 4 ingredients, and if you put them together in the right amount, you get the 0 bias peaks. And at the moment, there's no alternative explanation for these peaks as a Majorana, than a Majorana explanation. For instance, it's important to know that if you take one of these ingredients out, for instance, the spin-orbit interaction, if you line the field along that axis, you effectively take out the spin-orbit interaction, then it's gone. So it's really the combination of those ingredients that gives you the emerging Majoranas. All right. I'm looking at the time, and what I'm skipping is how you can actually use these Majoranas for quantum computing. But I promise it will take a long time. I think, it's 10 years. It will take me 10 years, so I can come back in now. But I promise to say something about the man, because there was this man in Toro Majorana. We now know that he was still living in the 50s. But what we did when we published, or when we submitted this paper to Science, we also submitted a suggestion for the cover. And so one of the students made a nice cover. I actually like this cover much more, with different versions, with the real device with nice colors. But one student actually had a creative mood. And then we put little blocks there, it looks, I don't know, kind of crazy, but the art director of science obviously liked it. Now this art director of science missed a thing, because what she missed was actually there was a hidden, I call it a hidden signature of Majorana himself. The title of the paper was Signatures of Majorana Fermions, but the cover actually had a hidden signature of Majorana himself. So you didn't see it. But if you look closely, and of course, where should you look for Majorana? At the end of the wire, of course. And if you zoom in, you actually do see it. There is Majorana, clearly visible in 2012, and that's how it looked a long time ago. So with this tribute to Toro Majorana, I would like to thank you for your attention and today's Friday afternoon. Thank you.